Okay, there we go. So, where was I? Um, Starting off with picking up the last bit from last lecture, there's one last thing that I wanted to cover in terms of the R tutorial. So I'll quickly kind of go through that. So, suppose we've got two tables here. So we'll call this table A. Can everyone see that? Yeah, great. And table B. Okay, let's say we have a column X and a column Y. And I'll have some values in here, A, B, C, D, 3, 4, 5, 6. And then in table B, let's say I also have columns X and Y, C, D, E, F, and we'll have values 7, 8, 9, 10. Okay, so you may sometime in the future be working with several different sets of data, right? And let's say that you wanted to merge them in some ways, right? So this is not altogether an uncommon task in data analysis. Maybe I have some like census data that I'm trying to combine with some other like location-based data, and then I want to combine them on the basis of one of the fields or columns or features, right, in my two tables. And so here, let's say I wanted to do some kind of intersection between table A and table B. So intersect on X. Okay? There are actually a couple of different ways that you can join these things together. Yeah, in some programming languages, they're called joins. In R, we call them merges. And I'm just going to quickly show the different types. Okay, so let's see here. Colors. Okay. So we can have kind of what you would expect, where the intersection only on properties where x's overlap, right? So this would be called an inner join. And if I were to combine these two tables together, what would the final table look like? Oh, sorry, I should call this, I'm making this confusing. I'm gonna call this one Z. Okay, so we're intersecting on X and then you have two different columns. Okay, so who can tell me what an inner join of these two tables would look like? What would the final table be? Any? Sorry, what was that? C and D. Okay, for your X, sure. So X would be C and D, and then the whole point of doing this merge is that I would bring along with it the properties corresponding to those values in my other columns. So now I would have Y and Z, and this would be 5, 6, and then this would be 7, 8. Okay, so this is kind of our classic merging type of operation, and that is known as an inner join. But actually there are a couple of other types of merges that we can do, and that being we can also do a merge that preserves all of the information from one of the initial tables. So this would be called a left join. And who can tell me what this table would look like? Any ideas? Yeah.
For X, you have ABCD.
Yep. A, B, C, D.
For Y, you have 3, 4, 5, 6.
3, 4, 5, 6.
Specifically for part Z, only for C and D, it's 7 and 8.
Yep, 7 and 8, and then you would have NAs in here. Okay. So that would be a left join, and the idea is if you wanted to concatenate data into this new data frame, but you wanted to preserve everything from one of the original tables, you can do that via a left join. There is, yes, also technically a right join. And I'm not going to make you guys guess. You can probably imagine what this looks like. This preserves all the information in table B. So my X will be C, D, E, F. My Y will now be, hold on, will be 5, 6, and there's no values for E and F. So these will be NA, and then my Z will be 7, 8, 9, 10. Okay, so I have my inner join, I have a left join, I have a right join. I also have a outer join, yes. Okay, and so that would look like everything. So my outer join will contain values preserved from both tables. So outer join will look something like this: X, Y, Z. And I will have A, B, C, D, E, F in my X. In my Y, I will have 3, 4, 5, 6, followed by NA and A. And in my Z, I'll start with my NAs here, and then 7, 8, 9, 10. Okay? Any questions about that? So this is a pretty common procedure. You know, it's something that you guys will certainly be doing at some point in this class, in the projects that you're going to be doing, and likely if you're doing any sort of data analysis, if you have to combine any data sets, you'll likely be doing operations like this. So I will show how to implement this in R real quickly. So let's build our tables first. So we're going to look at merging tables. So we'll have table A, exactly as I kind of described it. So we'll have a column X defined as A, B, C, D. And we'll also have a column Y, which is 3 through 6. And we'll have table B, data frame X equals C, D, E, F, Y, or Z equals 7 to 10. Okay. So here I'll show us how to do the inner join, where we say merge X equals table A, Y equals table B. So maybe I should have chosen different letters. So the X's and Y's here are not to be confused with the X and Y columns. This is specifying the two tables that I'm combining, and they are called X and Y in this function. And the column on which we are looking at where the values overlap is specified by this option called by. And so we're using by equals the name of that column. So if I run this, we should be getting exactly what we predicted and kind of drew out, right? So what I had said for inner join, which is we should see returned the overlapping the values that are intersecting in both tables, which are C and D, and the values corresponding to them in the other columns. So I hit enter, and of course I didn't run it yet, so here we go. So if you see in the bottom left in the console what has been printed out, this is exactly what I had specified, right? So in column X, we have the values C and D, which occur in both tables, and then the values will get populated out for the corresponding columns. Left join. Okay. Left join is almost exactly the same, except at the end of here, we're going to say all dot X. So the dot X refers to essentially keep everything from the table specified by the X, which is table Y or table A. So all X I'm going to say is equal to true, and I run this, and I will get the left join just as we specified. It keeps all of the data from the original table A, and then it puts in NAs for any values that weren't matched in table B. All right. Right join, as you can probably guess, very similar, except instead of all X, we say all Y equals true. Oops. I hit enter, and it is as we expected. And the last one that I'll say is outer join, which is, instead of all dot X or all dot Y, we just say all equals true. I run this. Yeah, sorry. I'm trying to catch up a little bit. But yeah, okay, so this is our final merge procedure, which gives us the outer join. Okay? Any questions about any of this? Yeah.
Scroll up to the first 3 lines.
Yes. Here, let me, I'll just do that. Yeah. And remember, all this code will be available online afterwards. Yeah, so again, this is probably among the more common procedures that are done. And so, yeah, get used to at least, yeah, so doing this type of thing, understanding kind of the principle behind it and how it works. I think it's not too complicated as far as this specific code. It is very useful, again, with the caveat that a lot of you guys who are familiar with R already, if you're using different packages that do joins or merges in slightly different ways, totally fine. In fact, there are more efficient packages to do these kind of joins. But yeah, the concept is really what's important here. Okay. Anything else? Great. Okay, so now we will jump into the content of our main lecture. And here, how do I clear the board? Here we go. Clear page. Okay, great. So today, we're going to do kind of our introduction and really kind of for the rest of, I would say about 90% of the rest of the class, we're going to be talking about regression. Okay, and so what is regression? Oh, let me use a better color now. So regression is modeling the relationship between variables. So I think I took a quick survey on the first day of class, right? But a decent number of you guys have taken some regression or econometrics class. And so this is going to differ a little bit in that we're going to focus mainly on application here and really sort of understanding. And one of the most important principles that I want to talk about is like understanding why we do certain approaches the way that we do. So I'm going to start off with a little example here. So let's do this. And I'm going to draw a couple of data points here. I'll put one up here. All right. I'm going to try something slightly new for this class. We're going to do some cold calling. So I'm going to toss this ball out. It's low pressure. If I'm asking a question that you don't know the answer to, you don't want to answer, you can pass, you can throw it to someone else, that's fine. Right now, actually, I want some volunteers to come up. So actually here, oh, whoever caught that. I'll give a more warning next time. Sorry, so yeah, I think you, yes. Come up to the front of the class real quick. And what I would like for you to do is give me your best shot at a best fit line. You can think about it however you want to do it, no pressure, and go ahead and just give us your best estimate. Okay, great. Go ahead and throw this ball to someone else. All right, we have contender number 2.
Is that it?
Yeah,
Okay.
thank you. Come on up here, don't be shy. Can you do a better job? We're gonna vote on who we think has the best line here, okay?
Well, I could do a different job.
You can draw whatever line you would like. Okay? Great. Nice straight line. Go ahead. One more. We're gonna do 3 people. We have our first successful catch of the day. All right. All right. So go ahead and draw me your best line. Any line you would like. You can be creative here too. All right. All right. Thank you very much. Round of applause for our 3 volunteers. Okay. So we got 3 lines here. Raise your hand for our first contestant, red line. Not even yourself.
I really like the blue one.
Raise your hand for the blue line. Wow, okay. And raise your hand for the dotted green line. 2, okay, you got a couple. Not bad. Okay, so we went with the blue line. And so, who can? I mean, there was a pretty. Right. It was pretty unanimous there. And so there must be something in common that you guys are thinking about that would make you kind of vote in this way, right? And so what criteria are you thinking about that makes you think the blue line is like clearly the best line? Who can, yeah.
I feel like it might have like the shortest average distance between the line and all the points.
Ah, okay. So who kind of agrees with that statement? Is that it's kind of the distance between the lines. So, okay. So if I were to, for example, look at, they make it really hard to change colors for some reason. Okay. So you're basically saying, okay, let me look at the distance from each of these points to my line, something like this. If I were to compare the like distance of those points compared to if I were doing, if I looked at the average length of like these, that's essentially what you're saying, right? Is like
Yeah.
that average, how far I am away from the points, looks like it's better for blue than for red.
Although in my head it was at like 90 degrees from the line.
Oh, so this way.
Just like whatever the slope of the line is
Oh.
perpendicular to the line between that and the point.
You're saying like this.
Yeah.
Well, okay, I can't draw very well, but yes. Yeah, sure. Okay. Yeah, go ahead.
I'm trying. I think when I look at this, I look at how concentrated the dots are. And
Yeah.
I would draw a line where it's most concentrated. And the ones that's really far away, they're like the outliers to me.
Okay.
There's not as much going on there.
But still having necessarily to do with kind of distance from the line, right? Yeah. Okay. Any other criteria that you guys are thinking about here? In that case, why don't I have a go at it? And via your criteria, I'm pretty sure I'm gonna win. Okay, here we go. Woo, 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 woo. Okay, there we go. Okay, great. So my line, okay, who thinks my line is the best? Yeah, right? I'm going through all the points, right? This is what you guys asked for, right? Which is distance from the points. I didn't say it had to be a straight line, right? So, you know, we have kind of ingrained in our heads, okay, I draw these like best fit lines in a certain way, right? But there are nonlinear lines, right? So no one did this, but it could have been, we could have had like some kind of line that looked like this, right? But there's actually an infinite number of fit lines that we could go through all of these points, right? And so I could have a line that goes like this. I could have a line that goes like this, that passes through all the points, right? And so if you were to look at my black lines relative to the colored lines that you guys drew, the criteria with which we determined what is the best fit, my line technically would do much better. Okay, and so we need to think about what the sort of objective measure is of a best fit. And what I would contend, right, based on this example, is that it's probably not just the distance from the line. There's other things that we might want to think about, right? And so I think you guys actually know the answer to this already. So what would be wrong with my line? Yeah.
It overfits.
Overfitting. And so overfitting is this idea that basically you've added too many parameters to essentially define that line. Okay, that's kind of a more sort of formal definition, right? But the idea is like if these points were coming from a particular like data set, right? And I were to add points that replicated, what we saw here, or, were points that were left out of that data set. Let's say a pretty reasonable point would be something like right here, okay? Here, the size of that error is like pretty massive, right? And so now the question is more about, okay, in addition to making the best fit for what we observe, how can we make sure we are not sort of overfitting? And that's going to be like one of the big themes of this class as we kind of walk through a lot of different techniques. A lot of what we're going to kind of focus on is thinking about this idea of what's appropriate for fitting under like these essentially two constraints. And we're going to formalize this idea a little bit later on in a couple lectures about how we balance this idea of like getting things to be as close to those dots as possible, but without overfitting. Okay? Any questions about that? Yes.
You can add to the definition of regression the word prediction.
Yeah.
It's not necessarily finding the line of best fit, even though that could also be regression.
Yeah. Well, so right now we're dealing in like kind of this 2D, easy to visualize. We'll think about that analogy more. And that'll be another big theme of this class. We're not quite getting to that discussion yet, but this idea of like certain types of models are best made to focus on the description of the relationship between variables, whereas other types of models are more meant to think about getting as good predictive outcomes as possible. And we will think carefully about those distinctions in this class as well. So good point. Those two things are kind of like the major themes that we'll be kind of running throughout this class. Okay, so let me clear all this. Yeah, all right, let me just go ahead and clear it. So, actually, wait, can I go back? Yes, I can. Okay. Oh, I need to get rid of all these things. Yes. Actually, so this is a nice little starting point. If I remove the ability to do all this like crazy waviness stuff and that we are focused only on best linear fits, okay, there is actually an objective way of getting to what is the best linear fit. And that is by exactly doing as I kind of described, which is you would be minimizing these differences. So minimize the distance. I want to do a quick aside based on a comment earlier about why is it that we minimize this difference like this as opposed to the perpendicular distance. The perpendicular distance like so. We always minimize based on the vertical distance. Who actually knows the answer to that? Anyone? So when we talk about linear regression, we are doing ordinary least squares regression. And so this is known as OLS for those who are not familiar. Um, but this is not the only metric with which we can measure those distances. Why do we look at the square of the distance? Does anyone know? Yeah, I see you raise your hand immediately.
I'm not sure how the words together yet, but if you don't have the squares, you might end up with negative values, so you're trying to avoid.
Yeah, you could actually have errors canceling each other out, right? Because they're on different sides of the line. And so that's not actually capturing the size of the total errors. So we can square them. But is that the only way to do it? What's a different way of making sure that they're not subtracting away from each other? Yeah.
Absolute value.
Yeah, you could do the absolute value. And so you could actually do ordinary least absolute value regression. That is a thing. But actually, we don't do that for historical reasons. Oh, yeah.
The main math isn't right. I was gonna say that squaring punishes outliers. Wrong, I thought that might be.
That is a feature of the way that this is done exactly, and so that's something that I would say kind of comes with the territory. Whereas an absolute value wouldn't necessarily punish outliers to the same degree. But actually, the reason why we do it as least squares is because for more historical reasons, doing the absolute value is analytically a little bit more difficult to do. And so if you're doing it as a square, you can actually come up with an analytical solution for solving for parameters of your OLS model. And so related to that, also, if you were to do these like perpendicular distances from the line, calculating those the length of those lines is, a little bit harder to do compared to your OLS. And so that's kind of the primary reason why we do it this way. It's having more to do with the computational complexity. Nowadays, computers would mostly be able to do this stuff pretty easily, and we kind of stick with OLS because there's such a large body of kind of momentum behind it. Okay? So I'll just say can do absolute value, but analytically difficult. Okay, any questions about that? So, let's kind of move on. So what exactly are we talking about here? We are talking about drawing a best fit line, straight line through these data points. And so I'm going to write a generic equation that represents, a line that would be going through these points. Okay, so we would have something like yi is equal to beta xi plus alpha plus epsilon I. And so this would be our unobserved error term. The I is referring to the ID of each individual point. Right, and so this is kind of the typical equation for a line. We have what's known as our beta coefficient, otherwise known as the slope of the line, and then we have our alpha, or intercept. So to be extra clear, there are different kind of variations of this equation that you might see. And so I want to be kind of as clear about the nuances and differences between these as possible. So I'm going to write out a couple more equations. So beta x plus alpha. This is the one that I just wrote down. So beta xi plus alpha plus epsilon I. Okay, let me write that a little bit more clearly. All right. So let me label these 1, 2, 3. 1, 2, 3. So equation 1 is a variation of this kind of general regression line that is essentially describing the true relationship between our y's and x's, okay? So don't mistake this for something that we're deriving or anything. Let us hypothetically suppose that there does exist a true relationship between y's and x's. And that would be represented by this kind of first equation. And it is essentially saying y is a function of x. It's equal to some slope coefficient of x plus kind of some intercept, right? And you can imagine this like true value outside of like hypothetical scenarios. This is something that you will never truly know, okay? It's not something that you can ever know with 100% certainty based on like calibrating to data. And the idea here is that we want our estimation of the parameters, right, so beta, to be equal to or to be as close as possible to this true values, true equation relationship as possible. Equation 2 is a representation of some kind of fit and how that relates to specific points of data. So now we're talking about real data. So I have yi's and xi's where, x1, y1 represent a particular point in that graph. Okay. And so let's take a look at, let's say this point over here. I can determine a line that fits through the data, and then I can say, oh, how do I get to that point? It is equal to some value of y, or I can use this point when I'm coupling my x times some kind of beta plus my alpha. So if I have beta times xi plus alpha, where would I end up? It would be somewhere on my fit line, right? So let's suppose we're going with the blue line. This is, let's say this is my xi value. and I'm trying to determine how that relates to my yi value, right? And so xi would end up on that point on the blue line, and then I would add the error term, which is the distance from my blue line to that, and then that would give me my yi. Okay? So equation 2 is about the specific relationship between points. And then the generalized predicted, and I should actually have little carets here. The little carets that I'm drawing over my y and my beta is specifying, actually there should not be a caret over the y. I'm getting myself mixed up here. I should be having this. Okay. The carets are indicating a predicted value, and so I don't get to know what the true beta or alpha is. This is what came out of my model. And then I can use these in conjunction with the information I have about x and epsilon to determine what that matching value of y is. Okay? 3 is kind of the generic version of 2, where if I wanted to predict a particular y outcome given in x, right, that's just what's based on the prediction line in equation 3. Yeah?
Sorry, I'm not understanding. So, just to recap, the first one just describes the relationship between x and y in general terms.
So yeah, but except that this is like, that's, 1 is what we strive to achieve, but we never can get there.
Okay.
That's like the true value. 2 is describing,
The relationship between points.
yeah.
And what does the caret have to do in number 2 again?
The carets are your best guess at what beta and alpha are, because you never get to know what those truly are.
Okay, and then number 3?
Is instead of thinking about matching to particular points, it's like thinking about the line as a whole, right? So what's the main difference between 2 and 3? It's about the missing error term. And so the error term lets us match the points in the data based on our prediction, and 3 is just, okay, now that I've done that and determined what my beta and alpha values are, I can actually make predictions about the whole line. Yeah.
Thank you.
So the name of the game here is the parameters, which are my beta and alpha. It's all about getting the beta caret and alpha caret, the predicted values of those parameters, as close to the true values as possible. So in a more theoretical class, we would then talk about the procedure with which we would actually calculate the betas. And there's a whole sort of proof that demonstrates if you calculate betas in a certain way, then you are actually going to be minimizing the size of those errors, right? The size of the distances between the points and the lines. So we're not going to get into that directly. Instead, I'm going to talk in practice, how do we sort of calculate these coefficients? So calculating coefficients. So there are specific procedures, right, to minimize the error. In general, when we are estimating parameters, there are 2 like general approaches that people think about. So one is doing a numeric method. And so numeric methods are kind of smart versions of guessing and checking. And so the primary way we would do this is with something like a gradient descent algorithm. And this solves for beta iteratively. This is a procedure where, okay, I take a guess at what beta is, and then I have some kind of procedure where I'm checking how kind of far off I am from a good answer, and then improving on my guess of beta as I sort of iterate through this algorithm. We also have analytical methods. So these are essentially solved optimizations. So this certainly isn't a full-on optimization class, but you know, as one way to kind of tie that concept together, right? All regressions are technically optimizations where we are trying to minimize or maximize something. In the example of a linear regression, we are trying to minimize the sum of all of those errors that are squared, right? The errors being the distance from the point to the line. So if you add up all of those errors and you're scoring them, that is going to give you a total error, and you are running an optimization that minimizes that. So optimization, you know, you've got objective function and some constraints, and so technically, if you're really good or you're really lucky or both, right, you might be able to come up with a like closed form solution. In other words, an equation in which I can do this calculation without having to do an iterative method. And so it turns out, and this is one of the benefits of doing the squared versus absolute value and or other ways, you can come up with a solution for your beta parameter. And so, you know, if you've taken a regression class, I'm sure you've seen this before. So it's xtx inverse times xty. So if you arrange your x's in a matrix, and then you do this matrix operation, this will give you a vector of the betas, which demonstrably will have the lowest error, lowest squared error, okay? There is no better line that you could draw than what would come out of this particular result, okay? Any questions about that? So, which way is better, the analytical method or the numeric or the analytical method? The one that has a closed form solution and you just get the values, or the one where we're guessing and checking? What do you guys think?
Analytical.
Yeah, so generally speaking, the analytical method is preferred, and actually when you run a linear regression in R, the default method will be the analytical, right? So this is like, why would I do a guess and check algorithm if I could do a closed form solution? And so in general, that's going to be true, but actually not always, okay? And so what is the exception case? So as it turns out, as we start to do more machine learning type things, when you are dealing with larger and larger data sets, what ends up happening is, so this particular analytical solution procedure where you're just like doing this matrix operation is very fast, right? It's a pretty simple operation, but you do have a matrix inverse in there. So that -1 is referring to a matrix inverse operation. That operation is actually fairly memory intensive, okay? And so in the area of, you know, big data sets where you're doing like these big machine learning type problems, if you're trying to run linear regression on things that have thousands, tens of thousands, maybe even millions of columns of different variables, this becomes memory intensive very quickly. And so actually, pretty interestingly, after many decades of mainly doing solving for betas with the analytical solution, big data analysis running these types of regressions have actually reverted to doing numeric methods. So gradient descent is actually still very fast and pretty efficient, and is not nearly as memory intensive as trying to come up with a matrix inverse. And so just a little caveat, if you happen to be running linear regressions that take a long time, it's likely because you are you're trying to do a regression on something that has many variables, and you might be better served solving it with a gradient descent. Okay? Any questions? All right, so let's look at an example of implementing linear regression in R. So how do we actually do this? Okay. So I'm going to prepare a couple of variables. Okay, I'm not going to call this deviation. I'm going to call this error. So all I'm doing here is I'm creating an artificial data set. Okay, and so our unif is a function that generates random numbers between 0 and 1. 0 and 1 is the default. You can specify a different range if you want. So here I'm asking it, pick 20 numbers between 0 and 1. I'm going to create an artificial error that's normally distributed. So I'm going to pick 20 draws from a normal distribution with a mean of 0 and a standard deviation of 0.1. And then I'm going to create my y's based off of my x and my error. So this is x times 0.5 plus error. That's not normally how you get data, where you just generate it. In this case, we get to kind of play like with kind of perfect information, right? And so I was mentioning before that when you have this idea of y equals beta x plus alpha, we never get to know those values, right? But actually here we do, because I made it up, right? And so I actually know what the true slope is, which is this, which is 0.5. Okay, so just keep that in mind. What does this look like? I can plot this like so. And y-axis. Okay. Oh, of course, I didn't run any of this yet. And hold on. Oh, I have two sets of arrows here. That's why that didn't work. Okay, here we go. Okay, so here's our plot of data of x's and y's. Great, and then, technically, if you wanted to, you could put in a line, and that would look, something like this. If you can set an intercept here, 0.05 with a slope of 0.45. So this may look kind of close here because our slope is 0.5 and our intercept is kind of close to 0, and there is no intercept in the true values. But we'll see if we can make a better line than this. Okay, so how do we actually run the regression? So we use a function called LM, which stands for linear model, and we are regressing y on x. Okay, so that is the terminology that we use. So if I run this and I can type in model fit and see what object came out of running that regression, and it will return this information. So it will tell me the call, which is essentially specifying the formula that I made, and then it will give its estimate based on the data of what it thinks the intercept is and what it thinks the slope value is. Okay. Oh, you know what? I am grabbing this from slightly the wrong figure. Okay, I'm gonna change this a little bit. It's not gonna make a huge difference, but we're just changing some of the numbers, just so that I'm using the same code. Yeah, I'm gonna make more data points here, so I'm doing 100 instead of 20 draws, and I changed the values a little bit. And I'm actually gonna call this for model 1. Oh, no, example model 1. If you are running the regression based on data in a table, you can actually do that as well, and I'll show the syntax for that. That'll be kind of more appropriate. So I'm going to make a data frame with a column named x equal to the values of x, and a column y equal to the values of y. And here I can call in that data frame and use, without quotations, the names of the columns in the regression equation, as opposed to calling the objects as vectors directly. Okay, and so all that's doing is I just made a table of the x and y's, and then I called the table. Okay, and so we looked at what's contained in that table. And actually, I'll do it again now that it's slightly different values. Yeah, okay, here. We had an intercept of 0.7, and then the slope is 0.4683 is the estimated. Right, and so we actually have a decent number of data points. There's like 100 data points, and yet we are not matching what we know to be the true value of beta. And so what is the true value of beta? 0.5, right? And we know that because we got to specify it. We made it up. Okay, so if I do summary example model 1, it's actually going to give me a little bit more information. So let's take a look at this. I'm going to do that again because I think it'll format it better. Yeah, here we go. So it gives a bunch of information here. And so in addition to what we saw before, it gives me information on the residuals, Who knows what residuals are? Any ideas? Okay, so residuals are simply the errors. So that is the size of the distance between my point and my predicted line. Okay. And so you have a bunch of residuals, right? Because you have many points. And so this is kind of the range of the size of the residuals. So it's giving you some summary statistics about that. And we'll talk more in detail about residuals and what to think about with that a little bit later. And we have now a whole bunch of other information in here. We have like the coefficient estimates, which are going to match what we saw earlier. But we also have these like standard errors and t-values and probabilities and tests of significance. We have, r-squared values, adjusted r-squared values. We have F statistics. Okay, so we've got a whole bunch of additional information. So let me pause here, and we're going to jump back over to our whiteboard so that we can talk about, what is that extra information that we're being given, and how, important it is. How does that help us understand kind of what's going on? Okay, so here we go. I'm going to draw two lines here. Okay. And okay, let's do something like this. So what I'm trying to do here is to create a set of points that mirror each other on the left and right, but are more spread out. And so the actual line between my left-hand side and my right-hand side are exactly the same. So assume that that slope is exactly the same. The points are simply like equidistant but farther away from the line, right? Okay, so let's say I wanted to oh my gosh. Sorry. So my line is influenced by the presence of all of these points, right? On the left-hand side, the points are closer to the line, and on the right-hand side, the points are farther from the line. And I'm attempting to essentially draw them in such a way that the lines themselves have the same slope. So now I have a question. If I were to take a point away, so let's say specifically this point that I've circled, which line is likely to change more? The one on the left or the one on the right? What do you guys think?
Right.
Yep. Yeah, exactly, right? And so the idea is there's like a larger contribution of error, and so the shift in that line as it readjusts is going to be larger because the farther away the points are, the kind of more influence that you have on what that line is doing. Okay. And in kind of the same way, we can kind of describe this as, well, even though these lines have the same slope, I'm essentially saying I'm more confident that the blue line on the left-hand side is like a better fit to the points than the line on the right-hand side, okay? And that is kind of the concept of your standard error, right? So if a point is taken away, which beta is likely to change more. So the idea being, which slope do we have more confidence in? And the standard error is like sort of a measure of that confidence. I'm gonna write the equation for calculating a standard error, and this is mainly for your reference, right? So we are an applied class. We're not gonna be deriving this. We're not going to be memorizing these things. You're just gonna be seeing standard errors like pop up as a output of the regression. But, you know, for completeness, standard error for a particular slope value or for a particular beta is equal to the sum of yi minus yi hat squared divided by n minus 2 over the sum of xi minus x squared. Okay, again, not something that you guys will have to remember, but if you ever need that as a point of reference, you can have that. Not to be confused with standard deviation, which we won't really talk about much in this class. This describes how the data itself deviates from the mean. So in this particular example, the standard deviation would be something like, oh, I have an average value in my data, and what does the spread of the data look like? That is different from what we are talking about, which is the standard error, which is how precise is our estimate of the mean. Okay, so difference being standard error is concerned about essentially how wiggly that blue line is, whereas the standard deviation is about like properties of the data. And to kind of further reinforce what I'm talking about here, when we think about our estimate of the blue line, right, maybe if I remove that point, the line might look something like this, or it might look something like this, right? So as you think about how the data varies, I might have some kind of estimates of my line that might be a little bit different. That like, I would say, okay, most of the time I think the line will be kind of within these bounds, okay? Whereas that range might be wider for the points on the left, and you might say, oh, most of the time I would think that our line is contained within something like this. Okay, so again, standard error is just about the like confidence we have in our estimate of the slope, okay, which is a made up value, right? It's not the true value, but we would hope that the true value would lay somewhere in that range. Any questions about this? Okay. Jumping back to our model results here, we have our coefficient estimates, and now we have these like standard errors. And the standard errors, let's think about the application of what we just talked about to, you know, this particular sort of estimate. It is saying that you can actually think about our guess of the slope as having actually a distribution, okay? And so we have, like our average guess we're saying is 0.468. But we're not saying that it has to be that value, that some proportion of the time we might guess that it is, you know, 0.47, or it could be 0.45, right? And actually there is a normal distribution about our estimate, and the parameters of that distribution are actually specified by the standard error. And so when it's normally distributed, we would say something like, so 0.46829, if you are 2 standard errors away from it, then, you know, 95% of the time, you know, we would expect our estimate to fall within that. So what does that mean? So let me just do this really quick. 0.46829 plus 0.03322 times 2, and we'll do this minus 2 as well. Okay. So going back to this thing, right? We are actually saying that there exists some possibility that the line looks like, you know, something different than what we drew, right? There is some possibility that the line actually looks like this. Technically speaking, there is some possibility that the best fit for these data points looks like this, right? But it would be a very, very, very small chance, right, that the line would actually look like that, given the points of data are arranged in this way, right? So in statistics, we never say anything is impossible, it's just improbable. And so what the standard error tells us that when we have plus or minus, let's say 2 times the standard error, right, in the normal distribution, 95% of our estimates of the slope should be between 0.40 and 0.53, right? That's slope value. And so, you know, realistically, we know the true value, right, which is 0.5. That's within the range, and so there's some percentage of the time that, you know, within our best guess range, actually, that we're getting the right value. Okay. Any questions about this?
Yeah, quick question.
Yes.
I thought you're, like, when you're doing OLS, you only have like one line that is the best fit.
Yes. Except that that line is so we are estimating what the best fit line is, right?
Okay.
And that estimate isn't actually just that one line and that's the only thing we get. It's actually a guess based on, with some probability associated with it. And that's what I'm talking about here. So this mean value would be what we consider the best fit line is. But the information you're actually getting from the OLS is actually more like all of this as opposed to just that blue line. In addition to us saying, here's what we think the best fit line is, you're also getting information about, okay, and in addition to this guess, I'm gonna tell you about what I think it could be and the range of values, what that best guess could be. Does that make sense? So, that is this standard error value, right? So that's telling us this like distribution of our guess. What about the t-value and then this probability greater than absolute value t? And what are these things telling us? Okay, so there's this common thing that people do, right? So who has heard of like tests of significance before? Yeah, a number of folks. So, I think that there's this very common thing that happens. You take these statistics classes or econometrics classes, and you get all this theory, and then when you go about kind of interpreting the meaning of results, there's this thing that happens where you focus on, okay, like, I've got like good, like the results are significant and I have a good R squared, and so this is a really good model, right? That's like, I'll guarantee that in your time in grad school, you'll go to some seminar and you'll hear someone say something like this. But the standard error and the R squared and these like metrics that we're using to judge the model are telling us specific things, and people often use them as like catch-alls for how good a model is, when that's not really what it's telling us. And so I really want to be clear about what the standard error is telling us and what the like test of significance is telling us. So I just described that, right, if you get this concept that like any slope is actually possible, we could, but that the standard error is telling us the like range of likely outcomes. There is a particular slope that people are interested in thinking about. And so does anyone know what that would be? Any ideas? It's the thing in which we test all slopes against. And that is slope of 0. What does it mean if you have a slope of 0? If your x is, yeah, so look at this, x versus y, and if the beta is equal to 0, then what does our line look like? It's a flat line, right? Horizontal flat line. What does that mean? Can anyone help me interpret that, like in the context of like, yeah?
Certainty that your line value.
It means that there's no relationship between your x and y, right? Because your x's will change, but your y's do not change. That's essentially what a beta of 0 means, right? So slope equals 0, x's change, no change in y, no relationship between x's and y's. And that's kind of the fundamental test that people talk about with a test of significance, right? So here, this particular example, I'm saying, we could, in theory, have this really big slope. And in the same way, in theory, you could have a flat line. And so what are the chances, given what we have gotten out of our model, right, with the standard errors, that the slope is equal to 0? In other words, that there is no effect. And so that's what the t-value tells us, that you would need to be 14 standard errors away in order for you to have a slope equal to 0. So the chances are very, very, very small. The chances are less than 2 times 10 to the 16th power that you would have a slope, that the true value of the slope is equal to 0. Yeah.
This is the term also for test of significance?
Yes.
Okay.
So the test of significance is referring to the probability that the beta is equal to 0. So here I told you the probability is, 2 times 10 to the negative 16th. So it would be the probability that the true value of the slope is equal to 0 would be 0.00000016 times 2. Okay, so very, very small. What the tests of significance are telling you is that number smaller than 10%? Or is that number smaller than 5%? Or is that number smaller than 1%? And that's an arbitrary boundary, that kind of distinguishes, it's like very unlikely that there is no effect, right? That the beta is equal to 0. And someone drew the line at 10%, and we call that 10% level of significance, or 1%, or 5%. But that's just kind of a arbitrary cutoff point. So sometimes you might have, this type of thing where the slope would happen 5% of the time, and we would say that that's significant at the 5% level. And in that particular case, it's up to your judgment. Is like the effect being 0, 1 in 20 times, like good enough? Yeah.
When you say that number, are we referring to the t-value?
The slope. The
beta.
Yeah, the beta is equal to 0. Yeah, so the t-value, so at the 5% level, it's t-value would be equal to 2 standard errors away. T-value is the number of standard errors to get to that value, right? And so this is what I'm talking about is here, in that particular example, we're saying that the slope, that this slope beta is equal to 0.46. Is that what it was? 0.468. And so you can think of this as a distribution, right? Where the mean is 0.468, and then the standard error is equal to 0.03322. And so, the likelihood that the slope is at this value, or let me use betas. So what's the likelihood that the beta is here, or here, or here, right? This is telling us that beta equals 0 is like way, way, way down there. That it is actually, in fact, exactly 14 sigmas away from the mean. Yeah, so very, very unlikely. Okay, any questions about that? Half question?
Half question.
Sure.
14 is from the t-value, or like where did the 14 come from?
Yeah, from the t-value. The t-value tells us how many standard errors away we are from 0, from beta equals 0. Yeah. So conversely, let's look at the intercept. The regression equation is estimating that the intercept is 0.67, 0.68, but the standard error is much larger, it's 0.93. So the likelihood that the intercept is equal to 0 is much higher, right? It's only 0.727 standard errors away, which corresponds to a probability of 40.47, 47%. So it's basically saying, I would actually expect that the intercept is less than 0 47% of the time. Okay. How does that square up with what we know the true value of the intercept to be? Normally we wouldn't know, but since I'm kind of playing God here, like what is our intercept value? 0, right? I didn't specify an intercept, so it's just 0. So actually, we could say this model's doing a pretty good job, right? Because it's like, how close are we to the true value? We're like less than 1 standard error away from 0.5, and we're less than 1 standard error away from 0. Okay. And that's as good as you're gonna get, right? With trying to estimate the true values. Okay, I'm going to talk about one more metric. So that the two common ones, right, that we always hear about when people talk about how great their regressions are is like, oh, all my things are significant, and then, oh, my R-squareds are great. Okay, and so let's look at R-squares. So what is the R-squared? R-squared is equal to the coefficient of determination. This is how much variation is captured by the model. R-squared is equal to 1 minus SS res. So this is the sum of the residual sum of squares divided by the sum of squares total. So this is just equal to, I'll write out more formally, the sum of yi minus yi hat squared divided by yi minus y bar. Okay, so that's the math. Let me explain this in a little bit more intuitive way. So we have our x's and y's. And all the R-squared is really doing is it is comparing, what if I just took the average value of y? Okay, and so I took all of those x's, all of the data points, and I just took the average in the y-axis, right? How, okay, not the best line. There we go. How does your best fit line compare with just a flat average value? What is the ratio in the sizes of the errors? Yeah.
Wait, what is the question you just put? The first one was what does the line look like if you take the average y, and then the second question
Yes.
after the second question was what?
So the second one is what we've been doing, which is you try and minimize the distance, right, from my line to the data points. The first one is all you do is, okay, let's say this is 1, 1.5, 2, 2.5, 3, 3.5. You just literally 1 plus 1.5 plus 2 plus 2.5 plus 3 plus 3.5 divided by 6. what is the average value of y's? Okay. So you take a flat horizontal line. You're basically saying, how does my fit compare against just the average values? That's what the R squared is telling us. Okay. It's not necessarily telling us anything about if the fit is making, sense in other sorts of ways, right? It's just caring about how much variation difference there is between my having a flat line versus having my fit line. Okay? So there's a particular sort of meaning to this, which is just describing the variation captured by the model. But again, like, imagine that there is a real relationship between my two things, but that it was just there's a lot of noise in there. Your model could be describing a very precise, it could be capturing that relationship in a very precise way, but your R squared could be really low just because of the artifact of the noise in the data, right? And so the R squared tells us, I think for those who are commonly used to hearing R squared describing how good a model is, just like forget that, right? It is about describing how much variation my model captures, and that is a different thing from how like good a model is, whatever that means, right? Because we could have a very good accurate representation of relationships between x's and y's, but have a poor R squared, and vice versa, right? You could have a really poor description of the relationship, but have, still a good R squared. Okay, any questions about that? So if I were to look here, we are going to talk about adjusted R squared later on, so don't worry about what that means. The multiple R squared is really what we're talking about right now. Here it's saying 0.6698, and so it's essentially saying that like 67% of the variation is being captured by my model, and the rest of it is not. And we know here that a lot of that is just coming, the rest of that variation is really just coming from the artificial error term that I introduced. Okay, any questions? All right, so I'm going to leave us with one last thing. So don't worry about following along or anything. Just going to talk about a particular example. So has anyone actually heard of the Anscombe quartet? No. Okay. So this is a don't. Okay, if you've heard of it, don't.
Is it ANOVA?
No, it's not ANOVA. This is an artificial data set used for illustrative purposes. Okay, so there are 4 sets of data in the Anscombe quartet, hence the quartet name. And we are going to run these 4 models. Okay, so I'm going to run a summary of model 1. And we're going to have someone talk to me about what they think about this model. Okay, so I'm going to go to the back here. Okay. Oh, sorry. Got to work on my aim. Yeah, so tell me what you think about this model. So, we can walk through some of the things that we've been talking about, and you give me your kind of best sort of judgment about what you think about this model.
So, what is the last column called again? The PR.
That's like the sort of test of significance, right? And so if you have stars, you're saying it's significant to a certain level.
So what I would say is the x1 from the last column is way higher than last time. So it's,
Okay.
I noticed that it seems to be less certain about the slope.
Sure, but it's still like significant at the, what is 2 stars, at the 1% level, right? So we have, okay, not as certain, but would you like?
It's still pretty certain.
Still pretty good.
When
Yeah, the intercept maybe not quite as certain, but still better than last time. Probably not equal to 0. And like, actually the r squared, like similar, right? 0.67. So like if you had to say on a scale of like 1 to 10, how good is this model? What would you say?
I would say it's maybe
Like an 8? Okay, yeah, it's like, it looks like a decent, decent model. We got things significant, not like at the like 0.001% level, but at the 1%, 5% level, and the r squared is like reasonably, reasonably high. Okay, please pass the ball to another victim. Okay, so I just did summary of model 2. So please tell me what you think about this model.
Kind of looks the same as the summary for the first one.
Pretty close, right? So 3.001. This is 3.0001, 0.5001, 0.5. It's at the 5% and 1% significance. Yeah, so okay, scale of 1 to 10. What would you think about this
8.
model?
Yeah,
8.
7.
Cool. All right. Axis 7 maybe. Okay. All right. Go ahead. Pass the ball off. Okay. We're gonna look at a different model, a totally different, completely separate model, calibrated to a different set of data.
It looks pretty similar once again.
Okay. Yeah. Similar estimate of the coefficient, similar slope, and so in your judgment, given similar standard errors, similar r squared, would your confidence in this model vary a lot from the first two?
Not really, no.
No? Okay. All right, one last volunteer, voluntold person. Go ahead, throw the ball. Oh, you're out. Okay, here we go. Last model. What do you think?
I still think it looks pretty similar.
Yeah, and so would you say anything different? Like nothing different necessarily in your confidence. All right, cool. Thank you. Okay. Great. So we're all in agreement. These models are kind of like the same. And really, our metrics that we looked at of standard error and r squared, right, mean that we can be sort of similarly confident in how good these models are. Oh, hang on. Figure margin's too large. All right, here's what the data looks like for our quartet. Yeah. So, this is a very sort of famous artificial data set that was constructed in a way to duplicate, these metrics that we often, we all too commonly rely on, which is these like tests of significance and r squareds, right? And so these do tell us something specific about what the model is doing and the results out of the model, but should not be used as catch-all terms for how good a model is. So hopefully this can kind of demonstrate that. Okay, and so that's it for today. We'll end here. Yeah, and I'll see you guys on Thursday.